Okay, hello everyone. Let's talk a little bit. Tonicity really has to do with the amount of solutes that's in water and referring to or help us to decide which way water is going to move. So with respect to diffusion of solutes and water, or diffusion of water, which is called osmosis, isotonic solutions here we're referring to the environment. Okay, so these are the environment, right? So this is the solutions here would be considered the environment. Okay, so I have it shorthanded here. So here, when a cell is in an isotonic solution, or when it's in something that's isotonic to itself, that means the concentration of solute in the environment is equal to the concentration of solute in the cell. So that means that the rate of diffusion outside of the cell equals the rate of diffusion in the environment, or into the cell. Okay, so out, in. All right, so if we look at a hypotonic solution, again, this is the environment. A hypotonic solution or hypotonic environment has a solute concentration that is less than that of the cell. So what this means is that the rate, okay, so here we have less, the environment has less, so it has basically more water. So basically the water is going to move into the cell. So here we have the rate out of the cell, or out of the environment in this direction towards the cell. Okay, so we'll put into the cell here. Okay, is going to be greater than that out of the cell. All right, so if we look at a hypertonic solution, it's just the opposite of a hypotonic solution. So this means that the solute concentration in the environment is greater than that of the cell. So the water is going to move again towards the hypertonic solution. So water should leave the cell. So we have the rate out of the cell and the rate into the cell is going to be just the opposite of the above. Okay, so the rate into the cell is going to be much lower than it is out of the cell until they reach equilibrium, of course. All right, so let's take a look at some examples. So here we have a beaker and it's filled with just water, right? So the water is the environment. So we'll just go ahead and put water here. Okay, so there's no solutes in this water. However, we have a cell here, and this is similar to your experiment in the lab where you used some dialysis tubing and there were cells made up. They were like mock cells, and it allows things to go through. Now, let's say that both sucrose and glucose can cross the membrane. Okay, so both sucrose and glucose can cross the membrane. And we can see here that we have a total of 5 molar solutes. Okay, so sometimes it's beneficial to add them up so that we know the overall movement of water. Now, which direction do you think water is going to move? So if you remember, this environment has less solutes. So what does that mean? So try to think about that. What type of solution is that with respect to the cell? So that's going to be, hopefully you said hypotonic. Okay, so that means the cell is hypertonic to its environment. So you can kind of say it the other way. So if the environment is hypotonic, then the cell is hypertonic. All right, so thinking about this in terms of osmosis, right? So remember, osmosis is the diffusion of water. And water moves towards the higher solute concentration. Okay, so water, since there's more water in the environment than there is in the cell, the water is going to move this way. Okay, so the water is going to move into the cell. Now, looking at the cell, since the cell is hypertonic and both sucrose and glucose are allowed to cross the membrane, what's going to happen is both sucrose and glucose are going to have a net movement of out of the cell until they reach equilibrium. Eventually, equilibrium will be met between these two over some time. Okay, so it's important to remember that osmosis, it's diffusion of water, and water moves towards the higher solute concentration. And solutes move towards the lower solute concentration. Okay, so it gets a little bit confusing. Let's see. Right, so now we have a cell which only has 2 molar of glucose in it, and the environment has 3 molar of glucose. So you can think of the environment as having water and 3 molar glucose. Okay, and then the cell also has water. However, it only has 2 molar of glucose. Which one has the greater concentration of solutes, right? So the cell has 2 molar glucose. The environment has 3 molar glucose. So the environment has a greater concentration. So you could say that the environment is hypertonic to the cell. And of course, then that makes the cell hypotonic to its environment. So since the cell is hypotonic, that means it has more water and less solute, so the water should move out of the cell towards the higher solute concentration. Eventually, this is all going to equilibrate because you can see that glucose is a higher concentration outside of the cell than it is inside the cell. So the glucose is going to move into the cell, and these are going to reach equilibrium. All right, so let's add some salt. Now we have a cell that has 3 molar sucrose and 2 molar glucose, so that's 5 molar solutes. Okay, and now we have an environment that has 3 molar glucose, so we know that there's 3 molar glucose here, and there's water. Okay, there's also water in here. All right, so we have 5 molar of solutes in the cell. We have 3 molar of solutes out of the cell. So outside of the cell should be hypotonic to the cell. Okay, and then that makes the cell hypertonic. So here we would expect the water is going to move into the cell, and these solutes are going to move out of the cell until they reach equilibrium. So we're talking about the net movement. So we've got solute molecules or sucrose molecules and glucose molecules moving out of the cell. The rate of movement out of the cell is greater than that of in the cell. So they're going to kind of bounce back and forth. However, the rate initially is going to be higher going out of the cell. Okay, so let's go ahead and look at another few examples, except they're going to be increasingly getting a little bit more complex. So here we have a cell. Okay, so we have this cell, and we could just add up the total concentration of solutes inside the cell. Here we have 0.05 molar of solutes. And then in the environment, we have 0.03 molar of solutes. Now let's say that fructose cannot pass the membrane, so this is going to stay in the environment. Now we have a greater amount of solutes, right? A greater concentration of solutes inside the cell than we have outside of the cell. So the cell is said to be hypertonic to its environment. Okay, and then of course the environment is going to be hypotonic to the cell. And we have a 0.03 molar of solutes, and it's got some water. Okay, So here we have water inside the cell. Ooh, water inside the cell. Now, remember, based on the definition of osmosis, remember it's diffusion of water, and that water moves towards the higher solute concentration, or really towards the hypertonic solution. So water would be expected to move into the cell at a higher rate than it is moving out of the cell. Now, if we look at the solutes, we can see that both sucrose and glucose are in a higher concentration inside the cell than they are outside of the cell. Remember, solutes move along their concentration gradient, so they move from a higher concentration to a lower concentration of solute. So the rate of movement of glucose and sucrose is going to be greater outside of the cell initially than inside of the cell until they reach equilibrium. Now, what's going to happen here, since fructose cannot pass the membrane and it's outside of the cell, this increases the concentration of solutes outside the cell. So basically, the sucrose and the glucose are going to reach or equilibrate so that the concentration of solutes in the environment is going to equal that of the cell. So the concentration of solutes, or the sucrose and glucose, might be slightly higher inside. All right, so let's look at another example. We've got a very similar example here. So we've got here, we can add it up, we've got 5 molar of solutes inside the cell. We have 3 molar of solutes outside of the cell. And we'll just keep this trend right here. We'll keep fructose. It cannot pass. Okay? So, if we look at this, we have 3 molar of sucrose and 2 molar of glucose, and that makes 5 molar of solutes, and then we have basically a higher solute concentration inside the cell, so the cell can again be called hypertonic to its environment, and then of course the environment is hypotonic to the cell. Now again, this is very similar. Again, this is just to reiterate what we discussed in the last example. So we can see that the 3 molar sucrose is going to move at a higher rate outside of the cell. The 2 molar glucose is going to move at a higher rate outside of the cell initially until they reach somewhat of an equilibrium. Now remember, there's 1 molar of fructose outside of the cell, so in the environment. So that can't cross. So there's still going to be that 1 molar staying outside of the environment, so that the sucrose and glucose would be expected to reach an equilibrium where inside the cell is still going to have a little bit more of both sucrose and glucose. However, the total concentrations, including fructose in the environment, would be expected to eventually reach an equilibrium so that there is an equal movement of at least those that can pass the membrane inside and outside of the cell. Another example, again, we have 5 molar of solutes inside the cell. Oh, and we have 5 molar of solutes outside of the cell. And let's say fructose still cannot pass the membrane. What do you expect to happen here? Okay, so inside the cell has water. Outside of the cell has water. They have equal solute concentrations, but fructose can't pass. What do you think is going to happen? So what I'm thinking is that the movement of water inside the cell is going to equal that that's moving outside of the cell. Okay, so we know that. Now, in terms of sucrose and glucose, there will be a net movement of slightly more sucrose moving out of the cell this way. However, fructose is there, so it's gonna equilibrate. Okay, so both of these, glucose is already equilibrated. Okay, so again, the rate of sucrose out of the cell should equal that inside the cell, so that it maintains that equal concentration on both sides. So really, you can say that these are isotonic. Alrighty. And there we go. Let's look at this example. Here we have 1 molar of glucose inside the cell, and we have 4 molar of fructose outside the cell. However, fructose still, again, cannot pass the membrane. All right, so what do you think is going to happen? So looking at this, we've got an environment that is hypertonic. Okay, and of course, the environment is hypertonic to the cell, and the cell is hypotonic to the environment. So the cell has more water, the environment has more solutes. So which way do you think the water is going to move? Remember, water moves towards the higher solute concentration, or basically it moves towards the hypertonic solution. So you would expect water, so this says water, okay, to move at a higher rate outside of the cell than inside of the cell. Okay, so we can do that. Fructose can't pass the membrane. So the water is going to keep moving out. The glucose will probably equilibrate as well. So we have this eventually equilibrating. However, the glucose is more likely going to stay inside the cell, right? Because all that fructose is on the outside. However, the water is going to keep moving out, so that the water is probably going to rise in here. And the cell is definitely going to shrivel up. Okay, so the water is going to increase in the environment because the cell is going to continually lose water due to such a high concentration of solutes in its environment. All right, so hopefully that gives you a good explanation of this. Again, if you have any questions, feel free to contact me and or come visit office hours.